Okay, so let's start the seminar. I'm very happy to have today's invited speaker, Dr. Hiroshi Kajino from IBM Research Tokyo. I just want to briefly introduce him. So he is currently a research scientist at IBM Research Tokyo, and he obtained a PhD degree in information science and technology from the University of Tokyo in 2016, and joined IBM in the same year. His current research interests focus on machine learning for molecules and spiking neural networks. So I think these topics are very, very interesting topics. So I'm very excited to today's seminar. So Dr. Kajino, please start your seminar.
Thank you, Yamada-san, for a nice introduction. And it is great honor for me to have a seminar. So let's get started. So the title of this seminar is a differentiable point process with its application to spiking neural networks. And the speaker is Hiroshi Kajino from IBM Research Tokyo. And this work was presented in the last ICML. And first of all, I want to mention that if you have any question, please use the chat box of the Zoom. And now I have a chat opening in another window, so I can check the chat anytime. So please feel free to post any question. And first of all, I'm going to introduce some opportunities and challenges in spiking neural networks to motivate our work. Because I think many of you may not are familiar with spiking neural networks, so it would be nice to motivate you to listen to this talk. So first of all, a spiking neural network is a little bit different from the current formulation of artificial neural network. And the main difference is that each neuron communicates with each other using spikes rather than using real values. And each neuron has its dynamical state called a membrane potential, which evolves in continuous time. So here is an illustration of a spiking neuron. So we have a neuron here and some signal, we have input signal by represented as a spike train. And also we have output signal here. And each neuron has a membrane, its dynamical state called a membrane potential. And this potential increases if it receives a number of spikes, incoming spikes. And once the membrane potential reaches to some threshold, this neuron spikes. It means it generates a new spike. It outputs a new spike. And then the membrane potential decreases to the ground level. So this is a basic formulation of a spiking neuron. And one opportunity to use a spiking neural network rather than the current artificial neural network is that its hardware implementations are often reported to be more energy efficient than using, for example, GPUs or other traditional mechanism. I think this is partially due to the efficiency of spike-based communication and partially due to the efficient information coding into spikes. But anyways, it is often reported that neuromorphic chips are more energy efficient than the other architecture. So this is the main reason why we focus on spiking neural networks. However, there are several challenges to deploy spiking neural networks into real applications. The first and probably the most significant challenge is that it is a little bit difficult to train a spiking neural network because it uses spikes to communicate with each other, and spike is a discrete object. So due to this discrete nature of spikes, I think there is no standard learning algorithm for a spiking neural network. So I think many researchers are pursuing more efficient and easy to train learning algorithms for spiking neural networks in the last 5 years in machine learning community. So this is a brief introduction of the opportunities and challenges. And we try to alleviate some of the challenges by developing a learning algorithm for a probabilistic formulation of spiking neural networks. So here is today's topic to be covered. First, I'm going to give a brief introduction to the theory of point processes, which serves as a mathematical basis of probabilistic spiking neural networks. And then I'm going to go into some introduction to spiking neural networks. And finally, I'm going to present our method. So first of all, I'm going to give a basics of point processes. By point process, I mean a temporal point process rather than more general point process. And a temporal point process models a collection of events. So let me first define the object that we are interested in, which is called event sequence. An event sequence observed during time interval 0 to t is denoted by calligraphy t. And this consists of events which is defined by timestamps of some discrete event, and as well as the information that there is no event during these time intervals. And this is quite significant because we have observation interval from 0 to t, and we have to encode the information that, for example, there is no event after event tn up to time capital T. So I think I have one question from Tanimoto-san, and I think it is related to spiking neural networks, so I'm going to answer the question in the next section. So yes, thank you for posting the question. So let me go back to the event sequence. So by calligraphy T, it denotes the set of events and the information that there is no event during these time intervals. And by using this calligraphy T less than equals to Tn, this denotes to a partial observation from time t to time tn. And temporal point process is interesting in modeling this event sequence in a probabilistic manner. And one approach to model this object is to define a probabilistic model of the next timestamp tn+1 given the partial observation up to time tn, which is denoted by this formulation. So by this probability density function, we can define that given the partial observation up to time tn, we can model when the next event occurs. And because this is a probability density function, it must satisfy these three constraints. The first constraint says that the next event tn+1 must occur after event tn. And the second constraint is is a constraint coming from the definition of the probability density function. And the third constraint says that we must have the next event with probability 1. So in order to model this event sequence, one natural way is to define this type of probability density function. However, in the theory of point processes, it is often a common practice is to use a conditional intensity function rather than a probability density function to specify a point process. And the conditional intensity function, lambda, is defined by this equation. Lambda equals to probability density function over 1 minus some cumulative density function. And first of all, I'm going to give some intuition to this conditional intensity function. Here I have, in the bottom of the slide, I have some illustration of the probability this density function, f. And what lambda models is the ratio from this portion of the graph to this small portion of the graph. And let me introduce brief intuition into this formulation. So suppose we haven't observed any event during this time interval from Tn to T, and we are now at time T, then lambda T tells us how likely the next event occurs now, I mean, from time T to time T plus dt. So by using the conditional intensity function rather than the probability density function, we can tell at any time T, we can tell how likely the next event occurs. And in the community of point processes, this definition, this specification of a point process is more intuitive rather than the probability density function. And therefore, this conditional intensity function is often used to specify a point process. And why we, and these equations tells why we have to define the conditional intensity function by this equation. So what we want to know is the probability of this this event. So given the event up to time Tn, and we haven't observed any event during Tn to T, and we want to know the probability of the next event occurs from time T to T plus dt. And this is written by the probability density function by using this equation. So we have the condition here, and we have the probability of this event here. And this the former part of this equation, it becomes the definition of the conditional intensity function. So we have this definition of the conditional intensity function. So in summary, although we can model a point event sequence by using a probability density function, it is more common and convenient to model probability density function by directly modeling conditional intensity function, because it is more intuitive, and also the constraints are more similar to those incurred to the probability density functions. So these three constraints are safely translated into these three constraints. So in order to model a point process, it is often used to a conditional intensity function is often used. I want to mention that this formulation is equivalent. These two formulations are equivalent. So from probability density function to derive a conditional intensity function is easy because by definition, the conditional intensity function is represented by probability density function. And the other direction, the proof is quite simple, so I'm going to go through it. So the most important equation is that the conditional intensity function can be represented by some derivative of this function. So this is easy to confirm because by differentiating this equation by t, we obtain this equation. So it is easy to confirm. So once we obtain this representation, by integrating both sides of this equation, we obtain this one. And by solving this equation by with respect to capital F, we obtain this representation of the cumulative density function F in terms of the conditional intensity function. And by differentiating this function by t, we obtain the probability density function representation of a point process. So in this slide, I introduced that these two formulations are equivalent. So it is safe to model a point process by a conditional intensity function. So in the following, all of the point processes are modeled by a conditional intensity function. And once we obtain a probabilistic model of an event sequence, what we want to do is to define likelihood of the event sequence and to learn a model from the data. So let me first introduce how to define the likelihood of the event sequence. So the probability density of the event sequence is defined by this equation by using the probability density function. The first term model is related to the probability density of the event at time tn, and the latter term is related to the probability that there is no event from time tn to t. And because this is written with respect to the probability density function, we can convert a probability density function into a conditional intensity function, and we obtain this formulation. So the first term is translated into this term, and the second term is translated into this term. So this is done by simply substituting lambda for f. And by summarizing the exponential term into one term, we obtain the final equation. So in this, this formulation is quite simple. The first n terms denotes are related to the events at time tn, and the latter exponential term is related to the probability that there is no event during the consecutive events. And this capital lambda is called the compensator, and which is defined by this equation. We have to, so I want to notice that this compensator is represented by some integrals of the conditional intensity function. But anyway, we can write down the likelihood of the event sequence by using the conditional intensity function by this formula. And once we have a likelihood, we can construct a learning algorithm for a point process. So the input is the event sequence and a parametric model of a conditional intensity function. And the output of the learning algorithm is a maximum likelihood estimator of the parameter of this conditional intensity function. And the algorithm is quite simple. It is just a stochastic, it's a gradient ascent for of the log likelihood function. So the first step is to compute the log likelihood function, and then using any tool to backpropagate the gradient to compute the gradient with respect to the model parameter, and update the parameter so as to maximize the log likelihood. And we obtain the maximum likelihood estimator after several iterations. And the algorithm itself is quite simple, but there is some not easy part in this learning algorithm. That is the computation of the compensator term, which is defined by this integral of the conditional intensity function. So, just because the input of the algorithm is a conditional intensity function, and it is not always easy to compute this integral. So this is a technical difficulty of learning algorithm for of a point process. However, there are, I think, mainly three approaches to address this difficulty. The first approach is to use integral friendly conditional intensity function. For example, by using a Hawk's process fits into this approach. And the second approach is to rely on Monte Carlo approximation, or use numerical integral to approximately calculate the compensator term. And I think this approach is practical because the integral is defined on one-dimensional space. I mean the time axis, and it is quite simple to approximate the integral by some numerical method. So this is quite, I think, practical. And I want to mention the third approach, which is quite interesting, which tries to directly model the compensator instead of the conditional intensity function. So the reason why this approach works is that differentiation is much more easy than integration. So by defining the model in terms of the compensator term rather than the conditional intensity function, we can compute this compensator as well as the conditional intensity function. So this can be computed by just differentiating this term with respect to t. And this was proposed by Omi et al. And presented in Europe. So, okay, so I have several slides left in the point process, and I have several questions in the chat box. I'm going to answer some of the questions. So the first question is from Tanimoto-san, and this should be answered in the next chapter. So I'm going to skip it. And the next question is the learning algorithm modeling spiking of a single neuron in the network. So I think this is also, this should be answered in the next chapter because it is related to spiking neural networks. And the third question is it straightforward for us to translate this lambda setter to a SNN that can be used for inference directly? So I'm going to answer this question. So probabilistic spiking neural network is defined by some parametric model of the conditional intensity function. So it is defined in terms of this conditional intensity function. So we can, so it is straightforward to define lambda setter for spiking neural network. And for in order to inference of spiking neural networks, that can be done by simulating the point process. And I'm going to explain how to sample from a point process in the next slide. So this will, I think this will answer this question. And the last question is, how does the method compare to the non-probabilistic method such as possibly STDP? So this question is also related to spiking neural networks, so I'm going to answer it in the next chapter. So yeah, but so anyway, thank you for many questions. So so far, I have explained learning algorithm for a point process and some difficulties and some approaches to address the difficulty. So once we have learned a conditional intensity function from data, what we want to do is to sample from such a point process, which corresponds to do some inference for spiking neural networks. So I want to explain some sampling algorithm. So so I think there are several approaches to sample from a point process, but I want to introduce one of them called a thinning algorithm, which was proposed by Luis in the 70s and Ogata in 80s. And the input of this algorithm is, of course, the conditional intensity function because it defines the point process, and it also requires us to have some upper bound of the conditional intensity function. And the output is a realization of the point process defined by this conditional intensity function. And in the right panel of this slide gives some illustration of this thinning algorithm. So I'm going to use this figure to explain this algorithm. So the main idea of the thinning algorithm is to generate enough number of events event candidates from a base Poisson point process and use the conditional intensity function to accept some of the events and reject the others, so that the output of the thinning algorithm is distributed according to the point process defined by this conditional function. So the algorithm is quite simple. So it repeats this procedure for a number of times. The first step is to sample the next event candidate from this base Poisson point process. And the second step is to sample dk, which belongs to 0 or which is 0 or 1 from the Bernoulli distribution with the parameter defined by this quantity. And if dk equals to 1, then we accept the event and add this event candidate to the output sequence. And if dk equals to 0, then we reject the event. So this is the basic idea of thinning algorithm. So this slide gives some intuition on why the thinning algorithm is correct. So what we care is this probability. So what we care is that this probability, if this probability equals to this quantity, then the thinning algorithm is considered to be correct. And this quantity is written by the product of these two probability. So this quantity is that given the partial observation up to time tn, and also given that there is no event from time tn to the current time t, this quantity measures the probability that the next event occurs from time t to time t plus tt. And this probability is defined by the product of these two probabilities. The first one is the probability that the base process generates the new event in time t in this time interval from time t to t plus dt. And this is the probability defined by this quantity. The latter probability is that the probability that this event candidate is accepted and is added to the list of the event sequence. And by and the product of these two probability is equal to this quantity. So we can prove that this probability is equal to this probability. So we can conclude that the thinning algorithm, the output of the thinning algorithm is distributed according to the point process defined by lambda. So this is a brief idea of the sampling algorithm. And finally, I'm going to introduce some extension to multivariate point processes by using the formulation of marked point process. So what we want to build is a probabilistic model of multivariate point process like this. So far, we are only caring about one sequence of events, but by multivariate point process, we are caring about a set of event sequences like this. Because in order to apply a point process to a spiking neural network, we have to have we have to model D. So if we have D neurons in a spiking neural network, we have to be able to model D sequences of events. So this is the reason why we are interested in multivariate point processes. And this can be modeled by a marked point process. So I'm going to first introduce a marked point process. So marked point process is an extension of a point process where each event is not only its timestamp t, but also it has a mark p, which is like a label of the event. And this event sequence of marked point process is modeled by this probability density function. And also we can define the conditional intensity function by this formulation, this formula. So it is quite simple to extend from a simple point process into marked point process. And the right panel of this slide explains how to model multivariate point process by using marked point process. So this illustration is quite intuitive to explain it. So a marked point process has each event of a marked point process has not only its timestamp, but also mark, which is denoted by, which is represented by the color and whether the diamond or circle. So we have two marks in this marked point process. Suppose we have a multivariate point process like this, and we can represent this multivariate point process by using this marked point process. So the translation is quite simple. So this dimension, the point process of the dimension 1 corresponds to this blue circle. And the event from the second dimension corresponds to the mark red diamond. And by using this conversion rule, this translation rule, we can translate this multivariate point process into marked point process. So the main message of this slide is that multivariate point process is represented by a marked point process. And also a marked point process is a simple extension of a simple point process explained so far. So it's straightforward to extend from a simple point process to a multivariate point process. So here is a summary of the point process. And so when encountering a sequence of events, try a point process. And point process is often modeled by conditional intensity function. And parameter estimation is easy if the compensator is available, but not so difficult if not, because we can rely on numerical approximation. And one of the sampling algorithm is based on rejection sampling. So this is a summary of the point process part. And I'm going to go into the part of the spiking neural network part. So here is a brief comparison between artificial neural network and spiking neural networks. The conventional artificial neural networks communicate with each other using real values between neurons. So this is quite common way to model the dynamics of the neuron. So we have one neuron and incoming signal, which is denoted by XM. And by computing the weighted sum of the input, the output of this neuron is determined. And both input and output are real values. And in contrast, a spiking neural network communicates spikes between neurons in order to compute something. So here is a spiking neuron, and the input is not a real value, but a sequence of spikes. And also the output of this neuron is a sequence of spikes. So this is a major difference between the conventional artificial neural networks and spiking neural networks. And why do we care about spiking neural networks? So the first reason is the energy efficient. So most of the neuromorphic chips mimic spiking neural networks, and often neuromorphic chips are reported to be more energy efficient. And here I want to mention the question by Tanimoto-san. So is it energy efficient in inference or also in training? So this is a good question. So currently I don't see, I think most of the neuromorphic chips are focusing on inference rather than training. So I think the training is done in some traditional computer, and the weight is transferred into neuromorphic chips so that we can do inference in more energy efficient way. So this is a trick of the current neuromorphic chips. So the answer is that the energy efficient is mostly in terms of inference rather than training. And training, the energy efficiency in training is, I think, open problem in this community. So I have some other questions. So is a learning algorithm modeling a spiking of a single neuron in the network? Yeah, I think I should answer this question in the point process at the last part of the point process section. We are going to model a spiking neural network by using a multivariate point process. Because suppose we have D neurons, and these D neurons generate a sequence of spikes by themselves. And these spike trains, the sequences of events can be modeled by multivariate point process. So, and once we can formulate a spiking neural network into multivariate point process, then we can use the learning algorithms or sampling algorithms that I presented in the former part of the talk. So I think this will answer this question. And we have another question: is in this formulation, can I say that such SNN is feed-forward only? I think this is also a good question. So the architecture is not limited to feed-forward architecture. And in fact, in my research, I use a fully connected neural network. So each pair of neuron is connected in a bidirectional way. So I consider the most general case where each pair of neuron is connected in a dense way. So, but some of the researchers are focusing on feed-forward neural networks. So this depends on the research. And another question: so do you have to set capital T or the number of spikes n? Can neurons have different number of spikes? I think this depends on hidden neurons or observable neurons. So I'm going to answer this question in the next section. Okay, so going back to the motivation of this work. So one of the motivation to focus on spiking neural networks is the energy efficiency. And here are some of the research questions related to this direction. The first one is, how can we implement a learning algorithm for spiking neural network based neuromorphic chips? So this is related to Tanimoto-san's question. So the current neuromorphic chips are mostly for inference purposes, but we want to enable neuromorphic chips to learn by themselves. And the second research question is how to train spiking neural networks so that they operate in a more energy efficient way. So this could be, so I think this is related to the hardware research as well as the software research. So we have to use both approaches to enable more energy efficient training. And the second motivation is that spiking neural network itself is, I think, interesting computational paradigm, because while the current neural network is defined in a static way, the spiking neural network is defined in a dynamical way. So we can encode information into the spike train, which has a time axis. So we can encode information into the temporal sequence. And also we can also use the temporal axis as a computational resource. So I know some of the research discussing on this perspective, such that the work by Mars in 1997 that reports that spiking neural network requires fewer neurons as compared to the current neural network in order to complete the same task. So, and this uses the temporal axis as a computational resource. So from these two perspectives, I think a spiking neural network offers an interesting way to compute in a novel way. So a research question related to this motivation is like, what kind of computation are spiking neural networks are better than the current neural network? And how can we efficiently encode information into the temporal axis? So these are our main motivations to study spiking neural networks. Here is a mathematical model of a spiking neural network. So we have two parts. The one part is a membrane potential model, and the other part is a spike generation model. So we are going to introduce some of the model in the next few slides. So the most basic model is a leaky integrate and fire model with deterministic spike generation. And the left panel introduces a leaky integrate and fire model, or LFI model. And this defines the dynamics of the membrane potential by this differential equation. So the membrane potential of the neuron D follows the dynamics of this equation. So the first term is a leak term, which exponentially decrease the membrane potential, and the latter term describes the influence of neuron D prime to neuron D. So here is a spike, incoming spike from neuron D prime, and we have a weight from neuron D prime to D, which is denoted by W, and this has some influence on the membrane potential. So this is the dynamics of the LIF model. And we typically use this delta function, this spike during representation by delta functions. So this is the LIF model. So this defines how the membrane potential increases or decreases in response to incoming spikes. And the right panel determines when this neuron generates spikes. And this explains some deterministic way to generate spikes. So a neuron D spikes at time t star if it reaches some threshold. So here, this illustration is more intuitive. So we have a membrane potential here increasing, and once it reaches the threshold, it generates a spike, and the membrane potential is reset to the ground level. So this illustration is defined by this mathematical model of a deterministic spike generation. So this slide explains the LFI membrane potential model and deterministic spike generation. And the next slide explains stochastic spike generation rather than the deterministic one. So here, a point process comes into play. So let me explain the stochastic spike generation. So in this model, neuron spikes follow a multivariate point process. And in order to define a point process, we have to define the conditional intensity function of the marked point process. And this is defined by this equation. So where this bold P is a one-hot vector, where active neuron has 1 and the other neurons have 0 in elements. So by this defines that the conditional intensity function is proportional to the membrane potential of each neuron. So this corresponds that the larger the membrane potential is, more often, more likely the neuron spikes. So this is the intuition behind this definition of the stochastic spike generation. And also we can, after spike, we can reset the membrane potential in a deterministic way. So this is a stochastic spike generation model of a spiking neural network. Finally, I'm going to introduce generalization of LIF model, which is called spike response model. So LIF model is defined by a differential equation, but a spike response model defines the dynamics of the membrane potential by using the convolution of some filter and the input spike sequences. The characteristic is that there is no differential equation, but only some convolution term. So the membrane potential of neuron D is defined by some base membrane potential and some influence from other neurons. And this influence is defined by some predefined function times some weight. So this is the formulation of SRM model. And by using this model, reset after a spike can be implemented by by tuning this filter function so that the influence from neuron D to neuron D, which means the self loop of neuron D, is negative for all the time. And this is a generalization of LFI model because if we define the filter function by this exponential function, then we can recover the LIF model. So so far we have explained some of several mathematical models of spiking neurons. So we have two models for dynamics of the membrane potential, and we have two models for spike generation. So the question is, which combination is the best for our purpose? And here I'm going to explain the design choices of spiking neurons. So the first choice is the LFI model versus SRM. So the characteristic of LFI model is that it requires us to solve differential equations. But in spike response model, we don't have to solve differential equations. So it is more computationally friendly. So we decided to use SRM with non-parametric model for the filter function. So this filter function is defined by a linear combination of some basis functions. And the weight by defining some weights for each of the basis functions, we can recover any type of function in theory. The spike generation model, we decided to use stochastic spike generation because if we use deterministic spike generation model, we have to solve the equation like this in order to determine the exact time when the neuron D spikes. In contrast, if we use a stochastic spike generation model, we can use the sampling algorithm of the point process to exactly simulate the spiking neural network without solving such a complex equations. So this is the reason why we use a stochastic spike generation model. So I think I'm very sorry that I'm running up the time. So I'm going to explain the ICML paper part in the next 10 minutes. So yeah, if you have any question, so I'm going to rush into this part. And also, I'm going to answer all the questions after explaining this part. So first of all, I'm going to explain the last section. So the problem setting of my research is explained in this slide. So the assumptions here is that all neurons are connected to each other. So we don't restrict the architecture to be feed-forward, but any kind of architectures are allowed. And we also assume that some of the neurons are observable and the others are unobservable, which means that we can observe spike trains are coming from a part of neurons, but some of the neurons we don't have such an observation. So these are unobservable. And what we are concerned about is given observable spike train, which is denoted by the calligraphy T O, we want to learn the model parameters of spiking neural network that can fit that will fit this spike train. So this is quite similar to unsupervised learning setting of to learn spike trains by using spiking neural networks. So this is the problem setting of this paper. And how can I solve this problem? And the first idea is to use the maximum likelihood estimation to estimate the model parameters of this spiking neural network. And because we have some hidden neurons, we have to rely on a variational approach to estimate the likelihood function, and which is done by Rezende et al. In early 2010s. And the idea is to define evidence lower bound and optimize it by stochastic gradient descent. So here is the elbow. So we have a variational distribution Q here, and we have log likelihood of the fully observable spiking neural network, and we have entropy term here. So the idea is to optimize this elbow with respect to the model parameter setter, as well as the parameter of the variational distribution, which is denoted by phi. And the existing approach by the authors is to apply SGD to optimize elbow. And in order to optimize this function, we must calculate the gradient with respect to setter as well as phi. And the gradient with respect to setter is easy to estimate by Monte Carlo estimation, because the differential operator can be safely exchanged with this expectation operator, and we can safely differentiate this term. However, gradient with respect to phi is not so easy to estimate because we have phi here. So this expectation operator itself depends on phi. And a common technique to estimate the gradient is to rely on the score function estimator, or reinforced technique, often used in the reinforcement learning community. So this gradient is computed by this equation. However, it is often shown that the variance of this gradient estimator is quite high. So we must apply several techniques to decrease the variance of this gradient estimator. So this is some limitations of the existing approach by Rezende. And a typical remedy, which is available in the late 10s, is a reparameterization trick, which is to make a realization of the variational distribution differentiable with respect to the model parameter phi, and to compute this elbow by applying automatic differentiation tools. However, there is no differentiable point process so far. So this is the main reason why I try to develop a differentiable point process in this research. And the idea of a differentiable point process is quite simple, which is based on the thinning algorithm. So the most part of the algorithm is similar to the thinning algorithm. And the difference is that whether or not, instead of rejecting or accepting each event from the base Poisson process, we assign some amplitude to each event. So we do not reject any event, but we assign some amplitude to each event, so that this amplitude encodes the information of how likely this event occurs. And this is done by replacing the Bernoulli distribution by Gamble softmax distribution. So the idea is quite simple, and by replacing the Bernoulli distribution with Gamble softmax distribution, we can obtain a differentiable point process. And the main contribution is to discuss some technical properties of a differentiable point process, but that is not so interesting, so I'm going to skip it in this presentation. And I want to mention several empirical studies. So the proposed method depends on two hypotheses. The first hypothesis is that the standard deviation of the gradient estimation by reparametrization trick is smaller than that of the gradient, the estimation of the gradient by score function estimator. So in order to validate this hypothesis, we design an experiment to estimate the gradient like this. And the second hypothesis is that lower variance of gradient estimator leads to higher predictive performance of a spiking neural network, which is intuitively which is correct, which should be correct from intuitive perspective, but which should be validated by empirical studies. So we also designed some experiments using synthetic data to validate this hypothesis. And this slide explains the results of the empirical studies. The first result is about the standard deviations of the gradient estimators. And this shows that our gradient estimator has much lower standard deviation by as compared to that of the existing method. So by this result, we can confirm hypothesis 1 is validated. And the second result discusses the predictive performance of our model, our learning algorithm compared to the existing learning algorithm. And the x-axis is the number of training examples used to train a spiking neural network, and the y-axis corresponds to the elbow evaluated on test set. And the higher the better. And at each number of training examples, our learning algorithm obtains a better spiking neural network. So by this result, we can confirm that the lower variance leads to a higher predictive performance. So we can confirm the hypothesis number 2. And finally, I'm going to mention a little bit about the computation time. So because our differentiable point process does not reject any of the event, the computation time of our learning algorithm is considered to be much higher than the existing algorithm. So we check the computation time. So this blue line is the computation time of the existing method, and the orange line corresponds to our computation time. And the x-axis is related to the number of hidden spikes. So as we increase the number of hidden spikes, then it requires much more time to train a neural network. And as we can see from this figure, our algorithm requires much computation time, about 3 times computation time as compared to the existing method. So this is apparently a limitation of our algorithm, and I want to address this computation time issue in future. So here is a quick summary of today's talk. So our contributions presented in ICML is a differentiable point process based on the thinning algorithm of a point process. And another contribution is a better learning algorithm of probabilistic spiking neural networks. And our finding is that our gradient estimator has smaller variance, and this smaller variance leads to better performance. However, we have some computational cost issue to be improved. So these are a quick summary of today's talk. And all of the codes are available under MIT license in this GitHub repository. So if you have any interest in this work, please visit and try some experiments by using the code. And yeah, I think this is the end of the talk. So thank you so much. And I'm sorry for running out of the time.
Okay, thank you very much for a very nice talk. It's very in detail that I really enjoy. And actually, there's a questions.
Okay, so yeah, I'm going to answer some of the questions. So, question from Honma-san: could SNN be freely mixed with analog neural network, like often happening in the brain? So I'm sorry, but I'm not so familiar with analog neural network or some biological neural networks. So yeah, I'm sorry, but I cannot answer this question. So yeah, I have to stress that my research interest is not in the relation to a biological mechanism of the brain, but I'm purely interested in the engineering perspective or engineering application of spiking neural networks. So yeah, I should be aware of some of the theory of the biological neural network, but yeah, currently I cannot answer this question. And the next question is about the relation between GIF and SRM. So also I don't know GIF, so I cannot answer this question. So I'm sorry. And is there any biologically plausible interpretation of your learning algorithm? The answer is no. So this is not biologically a plausible algorithm because it is based on back propagation, and which is often criticized to be biologically implausible. So this is not biologically implausible. And the next question, could you tell us more about some real-world applications of spiking neural networks? So I think the learning algorithm of spiking neural networks is not so applied in real world. And in most real-world applications, we train artificial neural network in the current by using some deep learning technique, and then transfer the weights of this neural network into spiking neural network, so that we can do inference on this neural network by using neuromorphic chips. So, and I think this is applied in vision community. So if you are interested in real applications of spiking neural networks, I refer to some vision application of spiking neural networks. But I want to stress that the learning is done on the current as a conventional artificial neural networks, and the weight is transferred to spiking neural networks. So there is no learning on spiking neural networks. So if not, so the next question, if not biological, local implementations are suitable for neuromorphic devices. So yeah, this is correct. So in order to obtain energy efficient implementation of learning algorithm on neuromorphic chips, it is the algorithm should be locally implementable. So we do not want to use some global clock to synchronize all of the neurons, but instead we want to use asynchronous mechanism to communicate, to let each neuron communicate with each other without any global clock. So yeah, this question is quite nice. So, and to the point, but the current algorithm is not so locally implementable. So this is an open question, I think. And is it same meaning of STDP? Is it needs to use special hardware or for spiking neural network? I think I can understand the question so well. So the algorithm is related to STDP, which so STDP can is one of the method to train a neural network in like a more like a heuristic way rather than the backpropagation based learning algorithm presented in this talk. STDP can be implemented in neuromorphic chips quite simply because it only requires some local operations between a pair of neurons. However, I don't see any specific real relation to STDP from our backpropagation type research. So I think if all of the neurons are observable, the resultant learning rules are similar to STDP, but I think they're not the same in when we have hidden neurons. And a final question, can spiking neural networks be used for combinatorial problems, for example, neural solvers for your, I don't know, it's the simple answer. I am not so familiar with a real application of a spiking neural network, so I am not, I cannot answer spiking neural networks are suitable for combinatorial programs or not. So yeah, I think this question is interesting. I'm going to Google some existing works solving combinatorial programs using spiking neural networks. So thank you so much. And we have additional question. Why do you call your method similar to backpropagation when it assumes neurons are fully connected? So in a real in a simulation in the experiment, we have we set some of the observable neuron by as input neurons and some of the neurons as output neurons. So, and these are not connected in a feed-forward manner, but these are connected in a bidirectional way. So the algorithm is similar to backpropagate the error of the output neurons to the input neurons, but the architecture is not the feed-forward architecture, but the error is propagated through the network. So not exactly the same as backpropagation, but the error is propagated to other neurons. So yeah, thank you for questions. So I think I have answered all of the questions here.
Okay. So it seems like there are lots of questions. It's really, really nice. And yeah, also actually, I really appreciate the very detailed explanation. I think I understand most of it. Thank you so much.
Yeah, that's nice.
Okay, so then let's thank the speaker again. Okay, thank you very much.
So, thank you so much.